All right, welcome to the video that you're going to remember for the rest of your life. The time where we really sat down and defined what it meant to take the Fourier transform. Okay, this is something you've been dreaming about since the third day of first grade when your teacher told you that Fourier transforms were going to solve all of the problems that you ever had in your life. We can start doing that now. So the goal of much of what we've been doing for the last few weeks was to be able to reconstruct the time dependence of a field, right, which we've called phi of x and t, from some set of initial conditions, which we generally have called like phi of x at 0. And we've done that by knowing that our modes, or our solutions to the wave equation, or our eigenstates, we've used a lot of different words for this, but that our modes contain something that we know something about the time dependence of those modes because they're eigenstates of the equations of motion, right, which tell us how things propagate through time. And so what we've wanted to do is we've wanted to decompose our initial conditions, right? We want to decompose phi of x on the initial slice onto these modes so that we can let each of the modes propagate through time the way we know it'll propagate through time, with omega determined by the dispersion relation. And you also know from what we talked about in our roundtable discussion and the video that you just watched on the delta functions that our eigenstates, that the states of this problem, the field with no boundaries and no rules, are 1 over the square root of pi times e to the I kx, where k can be positive or negative and have absolutely no value, absolutely any value you want it to, because again, no boundaries means no rules. And so the process is like this, right? I have some initial condition, phi of x and 0. I then need to find the Fourier transform. I need to find this set of basis functions, phi of k, such that phi of x and 0 is the integral of over all of the possible eigenstates times this set of amplitudes, phi of k, right? Where this amplitude is the continuous function of k because, of course, any possible value of k is possible, right? And that's why this is an integral over all of these states rather than a sum over states. Once I have that phi of k, I can then plug that back into my full solution where I have my states, my spatial states, right, times the time propagators, right? I can reinsert how each of these states is going to propagate through time, and then I have a simple, so-called, integral that will help me figure out what this field is going to look like at all times, at all places, right? This really reconstructs the entire solution from this set of initial conditions. Okay. And that's the procedure. That's what we really want to do. Now, how can we find those phi of k's, right? That's the tricky one. That's the hard one, is being able to figure out how do you solve for that function phi of k? Because once we do that, we just have to plug it into a formula, right? So that comes from, of course, starting with our definition of the decomposition, that phi of x, right, now these are my initial conditions, is a sum over my basis functions. I don't know how many times you've heard me say that, right? It's a sum, or an integral in this case, over my basis functions times this function phi of k. Anytime I want to extract amplitudes, anytime that I want to extract these expansion coefficients from an expression like this, I have to use the Fourier trick, which means I multiply by another, the complex conjugate of another eigenstate. So in this case, e to the minus I k prime x. You're probably, again, sick of me saying this, right? So I'm going to multiply both sides of this equation by that. I'm then going to rearrange my integrals. On the right-hand side, I see that the two basis functions give me, when integrated over dx, right, which is the domain of the problem, I get my Dirac delta function out. I then plug my Dirac delta function in, and I get an expression for these amplitudes. I get an expression for the expansion coefficients, right? I get an expression for this function that tells me how much of each basis function exists. That function is the Fourier transform, okay? And so what I end up with is the definition, right? And I should put 3 lines here. The definition of the Fourier transform is the representation of phi of x when I expand it onto my basis function defined by solutions to the wave equation. In other words, I'm taking this function of x, right? How is my field distributed through space? What does its configuration look like? And I'm decomposing it onto all possible wavelengths. I am, indeed, exactly doing what you always do when you look at something, right? You decompose it onto wavelengths, and you say, man, that's red, right? And that's what the Fourier transform is doing. It's saying how much of each wavelength exists in this field. Now, I can also do this the other way, right? And I can take, I can reconstruct phi of x given phi of k. Now, this is just the original decomposition. And for some reason, we like to call that the inverse Fourier transform, even though it really is the same thing that we started out with, but it's fine. So the Fourier transform is the one on the top, and the inverse Fourier transform is the one on the bottom. And you better believe that if you plug the bottom one into the top one, you get 1, right? I mean, you can't, you Fourier transform it, you inverse Fourier transform it, you have to start where you landed, okay? But if you ever get confused, especially because there's a lot of conventions in here, right? Where do the 2 pi's go, right? What is it, k or is it omega? There's all sorts of conventions that go into defining what's the Fourier transform and what's the inverse Fourier transform. I'm pretty much going to stick to this convention in class where I have the square root of 2 pi on both integrals in the denominator. You can always refer back to this to say, that's the Fourier transform, that's the inverse Fourier transform. And actually, if you come into my office any given day, I'm probably going to have this written down on a little slip of paper next to where I'm working, because I always have to remind myself what the conventions are and how the definitions go. And I actually probably spend half my time rederiving this to make sure that I really understand where it came from. And that's all there is to it. Now, a couple of different notes, and I think this is just to spark discussion and to give you the opportunity to ask me questions. I want you to remember that this Fourier transform phi of k always seems to be a complex quantity, right? There's no realness, there's no real operator on either side of this, and that's because these e to the I k x's are inherently complex basis functions. So even if my field is real, which is perfectly real, if I decompose that into the Fourier transform, I find that my Fourier transform turns out to be complex. And we'll get back to that. There's actually a particular symmetry that you get in the Fourier transform so that you know that the inverse Fourier transform is going to give you something real. But it's something to keep in mind, that there's no way around making the Fourier transform complex. And then the other thing I want you to note is that the phi of k's, the Fourier transform, contains exactly the same amount of information as the field. And in fact, if you go back and look at that slide, or you rewind this tape, I guess it's not a tape, you go back a little bit in this recording, you will see that there's this beautiful, there's this sort of similarity between the Fourier transform and the inverse Fourier transform that if you think about it for too long, you might get stuck in a loop to figure out which one's which, right? And that somehow they're perfect duals of each other. And that's something to ponder. That it's just another way of representing information, and that actually is pretty cool. Anyway, I'll leave you with this: the Fourier transform, the inverse Fourier transform. Congratulations.